Greetings, let's talk about a theorem about sequences here. So let's say that if the limit of a sequence xn has the value, let's say, capital X, and the limit of yn as a sequence has the value y, capital Y, as of course n goes to infinity, n goes to infinity, then if we add these two sequences, actually in the argument we basically connect them into the limit. So we have xn plus yn. Well, the limit should be that capital X plus y as a whole. So this statement, let's try to prove it, okay? So if one sequence goes to capital X as n goes to infinity, x sub n, and lowercase y sub n goes to capital case y, these are real values, real limits, real limit values. And of course this will, the addition of two real numbers, again in real numbers. So we want to see this proven. And we're going to follow the definition of a sequence. So basically a definition of a sequence limit, which basically means when we have a sequence, then there is this there exists for, let's say, capital case n is in real numbers, and then there exists that capital case n for any n higher than that capital case n, such that the difference between the limit value and the sequence term value is lower than epsilon. And epsilon is some positive number that is a real number also. Alright, so we have epsilon positive and epsilon real number, and there exists some capital case natural number n, that beyond that capital case natural number input, the term value will be smaller than any possible positive number epsilon in reals. It will be smaller, the difference between any term beyond the input of natural number capital N and higher will, the difference between that, the sequence term evaluated at that value minus the limit of the sequence at infinity will be smaller than any possible epsilon real number that's positive. So let's see about this. Well, that means that for xn we can find something, for xy we can find something. Let's say that I will not call this capital case n, but because you will also have to take care of yn, I will give them different names. So let's say first this is going to be n1 in this case, and then for the yn we'll do the same thing. So instead of capital case n, we'll now replace it by n1s. And this will stay, that's fine. And for and then also there is some n2 is also in natural numbers. There exists some n2. I mean, we could say there exists some n1 in natural numbers, and there exists n1 in natural numbers, and there exists n2 in natural numbers. That for every n that's beyond this n2, for the y sub n minus its limit value for yn, the limit value is y at infinity, is smaller than epsilon again. Well, now we basically stated the limit conditions, the limit definition for both of these sequences. It's very analogous, all right? So when we input a natural number n1 into xn or higher, the term at that point will be very close to the limit value, and the analogous thing happens for yn. And now let's take the limit. What's the trick? Well, we can take a absolute value and add the two terms, the two sequences like this, and also we can subtract the limit values, put it all into an absolute value. But this should be smaller or equal to, we can separate out this thing, so xn minus x, which is the epsilon very small difference about the sequence xn, plus an absolute value yn minus y. Just following arithmetics here, right? Now identifying its yn and capital case y. again, it's subtracted due to the arithmetics parentheses. The minus also appears here. And this is a property of absolute values. These broken down to absolute values should be higher, bigger, or equal to the size of this absolute value. But this was supposed to be epsilon, and this was supposed to be epsilon. So this is strictly smaller than 2 epsilons. And there's also a theorem that says, okay, we need the limit, the difference from the limit value of a very high term beyond some n1 or n2 or whatever, in that case, natural number beyond which we're looking. We need that value to be this epsilon to represent a very small real number. And the difference between that term xn and then very high value and the limit value x is smaller than any possible epsilon. But if it's smaller than any 2 possible epsilons, it's also very small, right? That epsilon can be arbitrarily small. And there's this sort of corollary we can talk about in another one perhaps, but it says constant value real number multiplying epsilon can still be very small value, and it's seen as valid as epsilon itself. So we have 2 epsilon, that's just as fine as if we had epsilon. That's sort of the idea here, right? So we saw, okay, some k times epsilon, or some constant times epsilon, some c perhaps times epsilon, is strictly bigger than the addition of these 2 values, right? And but because these 2 differences represented the condition for the limit for those individual 2 sequences, if they're added and they're still smaller than epsilon, that also says that yes, it is actually correct. If we add it together, which we had right here, the term where the 2 sequences were added together and their limits were added together in other parentheses, then that arithmetic actually let us return back to the expression where it's separated out. We still saw that's also small value. That's proven that this statement is indeed valid.